Hello students, good day all. The continuation of oscillations. In this session, we are going to learn energies in SHM and the oscillation due to a spring, the graphical representation and the simple pendulum. These are all elaborately we are going to learn, children. Let us go. So energy in SHM, that is through kinetic energy and the potential energy we are going to see, because the total energy which is equivalent, the energy in the harmonic oscillator, it has partially kinetic energy and partially potential energy. That is, if suppose the body is displaced from its equilibrium position, by doing work upon it, it acquires potential energy, right? Now, the body is released. It begins to move back with the velocity, then it acquires the kinetic energy, right? Now, for the kinetic energy, we'll see, as we know the displacement, that is x which is equal to a cos omega t plus phi naught. This we know, right? And for the velocity, v which is equal to dx by dt, right? So we need to differentiate this. We will get, after differentiating this, minus omega a sin omega t plus phi naught, right? Now you will get for k which is equal to half mv square, right? Then half m omega square a square sin square into omega t plus phi naught. Then here, as we know that a square sin square omega t plus phi naught, which is equal to a square 1 minus cos square omega t plus phi naught, right? Then we will write a square minus a square cos square omega t plus phi naught. Now, here k, the kinetic energy k, which is equal to half m omega square a square sin square omega t plus phi naught. This is the value, right? Now the k value we will get half m omega square a square minus x square. So we'll get ke kinetic energy which is equal to half k into, we will get a square minus x square. Right, children? Yes. So now for the potential energy, here the potential energy when the displacement of the particle from the equilibrium position of x we have taken means the restoring force acting on it, that F which is directly proportional to x, so that F which is equal to minus kx, right? So this dw, this we have taken for that, if suppose we displace the particle further for the distance of small distance dx, so we need to know about the work done. So that the work done against the restoring force which is given by dw which is equal to minus f dx, so that plus kx dx. So the total work done if we need means we need to integrate it. So the w which is equal to integration of dw which is equal to integration over 0 to x. So we have taken this from the mean position. So x which is equal to 0 to the displacement x. So that this we have taken the limits from 0 to x. So integration of 0 to x, kx dx. K we have taken the constant out. When we integrate it, we will get x of dx, x square by 2. By applying the limit, right, we will get half kx square. Got it, children? Now, the work done which is against the restoring force, which is stored as always what we said? Potential energy. So that U which is equal to half kx square, that is equal to half m omega square x square, which is equal to half m omega square a square cos square omega t plus phi naught. This and all we have taken from previous knowledge of the expression. So the total energy is what we have said already, that is the partially the kinetic energy and the potential energy. Together we will get the total energy. Then U which is equal to K plus U. So that half K A square minus x square plus half kx square. Graphical representation. This is for energy in SHM, right? See, the graphical representation we have taken for at mean position, which is x which is equal to 0. Then at that time, kinetic energy will be half Ka square. Because of this will be 0, then half Ka square will come. So x will be get 0. But here the potential energy which is equal to U is 0. Right? Versus at the extreme position, x which is equal to plus or minus a we have taken. So Ke which is equal to K, that is equal to half K a square minus a square, so that 0, kinetic energy is 0. The potential energy U which is equal to half Ka square. Now observe the graphical representation which is there. It shows the variation of the kinetic energy K, potential energy U, and the total energy E with the displacement x. Then the graph for K and U are parabolic, right? While that for E is straight line which is parallel to the displacement, you are seeing that, right? E which is equal to K plus U, right? So, then the energy is all kinetic, and for x which is equal to plus or minus a, then the energy is all potential, right? So, we are seeing here the next graph that shows the variation of the energies K, U and E as of the harmonic oscillator with time t. We are seeing that clearly that it's twice in each cycle, both kinetic and the potential energies, which is assume their peak values. So both of these energies are periodic function of time. The time period is begin, each of we have taken here t by 2, right? Now oscillations due to a spring. See the horizontal oscillations of a loaded spring diagram which is on the screen. You can take that the massless spring which is lying on the frictionless horizontal table. So actually it is attached to a rigid support, one end which is attached to a rigid support and the other end of the body which is attached to a mass m. If the body is pulled towards right through a small distance x and it is again released, means it starts oscillating back and forth about its equilibrium position, which is under the action of the restoring force of elasticity. Then we can say F which is equal to minus Kx, where K is the force constant of the spring. Here the negative sign indicates the force which is directed opposite to x, right? So now if d squared x by dt squared is the acceleration, so m of d square x by dt square which is equal to minus kx, right? So d square x by dt square which is equal to minus k by m x, which is equal to minus omega square x. Here the acceleration, this shows the acceleration is proportional to the displacement of x, right? It has acts opposite also. So the body executes a simple harmonic motion. The time period which they have given T which is equal to, we know that the basic formula is 2 pi by omega. So 2 pi omega, the value which is root of k by m. So T which is equal to 2 pi root of m by k. The frequency, the base formula which is equal to 1 by T. So that 1 by 2 pi root of k by m, right? Simple pendulum. See, the small oscillations, the motion of a simple pendulum in the simple harmonic motion which we are going to see. See the diagram, children. The simple pendulum consists of a point mass which is suspended by a flexible and inelastic and weightless string from a rigid support of infinite mass. See, in practice, we can neither have a point mass nor a weightless string. See, in practice, a simple pendulum which is obtained by suspending a small metal bob by a long and fine cotton thread from a rigid support. Right, this we will do as an activity also, right? So this expression for the time period, see the equilibrium, suppose the position which is equilibrium, then the bob of a simple pendulum lies vertically below the point of the suspension. If the bob is slightly displaced like this, which you are seeing on the diagram, either side, and it is released, it begins to oscillate about the mean position. Suppose at any instant during this oscillation, the bob lies at position A when its displacement is OA, which is equal to x, and the thread makes the angle theta with the vertical. So the forces acting on the bob then, weight mg of the bob acting vertically downwards, the tension T along the string. So the force mg, which has two rectangular components, that is the component mg cos theta that is acting along the thread, which is balanced by the tension T, right? And the tangential component mg sin theta, which is net force acting on the bob and tends to bring it back to the mean position. So the restoring force F, which is equal to minus mg sin theta. So minus mg, the theta will be, it will come through that oscillation, theta minus theta cube by 3 factorial and theta 5 by 5 factorial minus plus like this. It will come till n number of oscillations, right? Now, which is equal to minus mg into theta. So we can take it out. This 1 minus theta square by 6 plus theta power 4 by 120 minus till the end it will be mu, right? Now where theta is in radian. So it's clearly we know that the oscillations are not simple harmonic because the restoring force F, which is not proportional to the angular displacement. So if theta is very small, then the higher powers we can neglect this. Then F, which is equal to minus mg theta. We have taken here the L is the length of the simple pendulum, then theta in radiant, the formula is arc by radius. So that is equal to x by L. See the diagram. So x by L. So F, which is equal to minus mg x by L. So R MA, F which is equal to MA. So that MA which is equal to minus mg by L into x. So we need A, that acceleration A which is equal to, by rearranging this equation, we will get A which is equal to minus g by L into x. That is equal to minus omega square x, right? So the acceleration of the bob, which is proportional to its displacement, and it is directed opposite to that also. So for small oscillations, the motion of the bob is simple harmonic. So the time period formula is what? T, which is equal to 2 pi by omega. So the omega value we have taken here, 2 pi by root of g by L, or T, which is equal to 2 pi root of L by G. So the time period of the oscillation, with the help of this formula, we can deduct through the simple pendulum, right? Yes, students. So far we have learnt about the energies in the SHM. That is the total energy, which is equivalent to the partially kinetic energy and the potential energy. For the derivation we have done, and the graphical representation and the energies in SHM. Next to that, we have learnt about the oscillation due to the spring. For that graphical representation also we have learnt, and simple pendulum. The simple pendulum time period we have derived. Thank you children.